David Smith here with one more flipped classroom math video for your enjoyment. 3 tips. First, you can speed up or slow down the playback if that helps you follow along. Second, you can pause anytime to catch up with your notes or think a little harder. Lastly, you could turn on the captions, which will show you my words on the screen below. Today's lesson is going to give you a little bit more practice with domain and range and functions, and we're going to talk about how to answer questions using our calculator, sketching your graph on paper, and then finally answering questions about domain and range. Also, we're going to take a look at piecewise functions and dive a little bit more deeply into how you note them and how you analyze them. Okay, here is our first function. And it's listed in factored form, and you can type that into your calculator, no problem. You don't need to do the expansion and turn that into a cubic function. But you should recognize that it is cubic. We have 3 x's, so we're going to wind up with an x cubed in our expanded version if we did that. So that's going to make a very certain type of graph, which you'll see in a minute. So what I want you to do right now is pause the video, enter this function into your calculator, and then center your graph in such a way that you can see the important parts of that function. Okay, so let's take a look. What I did is I took my graph from my calculator and I transferred it onto the board. Okay, so I want to talk about what that means. You might need to look at one of the help videos that are on YouTube for using calculators to do all this stuff. Okay, so this is a sketch. However, you want to capture the important points on the function. So we've got 4 intercepts. This is a cubic function, and a lot of cubic functions have local maxima and minima before they shoot up or down forever. Okay? So you want to capture your intercepts. So I've got an x-intercept there, there, and there. And then you want to capture your y-intercept. There's one there. And then you've got this local maxima here and this local minima there. Okay, so you can use the trace function, you can use the zeros function. Depending on which calculator you use, you'll have to take different steps to get the coordinates of these points. But these are critical for this function, and a fully fleshed out sketch will have that. Okay, so if you need help with your calculator, reach out to me in class or get on YouTube and do a search for finding intercepts on my, and then list your calculator. And you're going to find a lot of videos out there that will help you do that. Okay, so what I've done, just to summarize here, is we used the GDC calculator to graph the function. GDC stands for Graphing Display Calculator. So we pulled up the calculator, we entered the function in there, we saw it on the calculator, then we used the calculator's tools to grab the intercepts and the maxima and the minima, and then we sketched our graph on paper. Okay, so that's step 2. Now let's take a look at step 3. Okay, I want you to stare at this graph or stare at your calculator and tell me what the domain and the range are. And let's just review that real quick. The domain is all the possible x values that can be in that function. So you've got a graph, you see what it does, you can make a very definite statement about what x values are allowed or will be in that function. And then the range is the y values. And so again, you can look at that graph and you can see very clearly what kind of y vowels you get out when you put the x vowels, that's good, values in the function. So pause the video, think real hard, write down the domain and the range of this function. Okay, let's walk over here and take a look. Here's my domain, here's my range. Take a look at what you wrote down, see how you did. Check it out. There's no limit on either one of these. For the x values, this function is going to go as far to the left as it can, which is to infinity. So there's no limit into what we can put in for x. It can get as negative as it needs to. And then this arrow is also trending right to infinity. So there's no limit left or right, positive or negative, for the function. So we've listed the domain as negative infinity to positive infinity exclusive. So it never gets to infinity. You can't get to infinity. So that's why we have the brackets facing outward. Or with the other notation, we can just use parens enclosing the two infinities. But I'm going to propose that we stick with this notation for our class. It's the simplest, it's clear. Okay, same with the y values, the range. There's no limit. This function is going down as far as it wants. It goes down into infinity. So y can be as negative as you want it to be. And the same thing as the function is going up forever. So it can be as positive as it needs to be. So just like with the domain, the range is exclusive of negative infinity. Can't quite get there, but it can go as close as possible. And on the positive side, it's positive infinity. So this function kind of doesn't have a limit on the domain and range. It can be any real number for both of those. All right, let's try another one. Now this function is a rational function, and if you've never played with rational functions before, you're going to get an interesting looking graph. Just stay with it, see if you can figure out what it's doing. So here we go. It's x minus 3 over x plus 1. It's a fraction. Typically, or most certainly, it's got an x in the bottom of the fraction. So that's one of the things that makes it a rational. Remember, rational numbers are numbers that can be written as fractions. So here's our function. F of x is x minus 3 over x plus 1. What I want you to do is do step 1, pull out your calculator, graph that function, zoom that window around so you can capture what that function's doing, and then make a sketch of the function based on your graph with any important numbers labeled. Okay, I warned you, that graph is definitely different. If you haven't looked at rational functions before and looked at their graphs, you're probably scratching your head just a little bit. Okay, so check this out. This is the graph I get out of my calculator. And whenever you have a rational function that does something like this, we've got a binomial on top divided by a binomial, you get two curves. You get a curve that's in one quadrant, in this case it's in the second quadrant, and then you get a curve here that's in the fourth quadrant. Okay, so it's always going to be opposite of each other, and sometimes they cross the axes and you get intercepts, and sometimes they don't. So this curve is not crossing the x or y axis, so no intercepts on that curve. This one crosses both axes. It's crossing the x-axis at the point 3, 0, and it's crossing the y-axis at the point 0, negative 3. Okay, so I grabbed that from my calculator. Now let's talk about the dashed lines. They are called asymptotes. A-S-Y-M-P-T-O-T-E-S. And that's this line is an asymptote, and so is this line. Okay? So an asymptote is a horizontal or vertical line that a function gets close to but never touches. Okay? It's never going to touch that. So if you check this out, this function, when it's going to the left, it's getting closer and closer and closer to this line, y equals 1, but it never touches it. Okay? Okay, this is tricky. The thing to realize before we get into what I've written there is that the only thing x can never be is negative 1. It's approaching from the negative side. It gets really close to negative 1, but it never gets there. Same thing when it's approaching from the positive side. It goes really negative for y, but it never gets to negative 1 for x. You just can't get it. Okay? So, what this is saying is exclusive, negative infinity to negative 1. Now the bracket is facing out, so it means it can't be negative 1. And then we have an and, that's for this curve. Positive infinity, because this one goes out to positive infinity, but it can't get to negative 1. So that would be the limit on that side. So really, this one can be better expressed with set notation. This is the set of all x such that negative infinity is less than x is less than positive infinity, comma, x not equal to negative 1. That's a much better way to say it. It's more elegant. This is kind of kludgy because we have this range and we have this range, and it doesn't really tell us the essential thing is that x can be anything except negative 1. There's just one limit on the domain. You can't put negative 1 in there. And why is that? Look at your function. Why can't we put negative 1 in there? -1 would make the bottom of this fraction 0, and we can't do that. So this is very real mathematics, but we can't have x be -1 because the bottom is 0, and that's what creates that vertical asymptote, okay? All right, so now pause the video, think real hard about the range. This is the y values. If you understand this, that's going to give you clues for what goes there. So give it a shot. Okay, so I used the same technique we used with this, but now I'm looking at y equals 1. So the range, these are the y values. It can be negative all the way down to -infinity, and that's this limb going all the way down. But it can't be 1. We're never going to get 1 out of this function. So here's, this part pertains to this curve, right? It can go -infinity all the way down, the y value. We're talking about the up and down. And it can go all the way up, except it can't quite get to y equals 1. This part of the function, this curve, is expressed here. Okay, so it can get, as we go negative with x, it's getting down all the way, but it can't quite make it to 1. So that's our limit. Can't be 1, but it can go all the way up to infinity. Okay, so that works. So that's why we have infinity there. So see if you can write it in set builder notation. So take this, look at how this translated, and see if you can write it that way. So very similar. This is the set of all y, such that basically y is between -infinity and +infinity, but y cannot be 1. So there's our set builder notation for the range of that function. Here comes a piecewise function. And these are just kind of interesting / strange / maybe a little bit more complicated functions. But all you have is you just have, in this case we have 3 functions that govern different ranges or different domains for x. Okay, so let's check this out. We're defining f of x as 3 different functions. There's 2x, there's 4, remember that's a horizontal line, and then there's 1/2 x plus 2. So these 2 are linear equations. They're lines that have slopes and intercepts. And then this one is a horizontal line that's just y equals 4. F of x equals 4 is the same as y equals 4. So we have 3 functions. Now we have ranges for x for which that function is active. Okay? So when x is between 0 and 2, our function is 2x. Now as we move up, when x is greater than 2, but less than or equal to 4, then our function is f of x equals 4. So for a little while, it's 2x. Then it becomes 4. That's this range. And then finally, when we pass 4, when x is greater than 4, but less than or equal to 8, the function changes to 1/2 x plus 2. Okay? So you're going to need to watch the video for how to put in a piecewise function. I'm going to put a link for that below in the comments so you can click on that. It's totally doable in both the TI-84 and the TI Nspire, and you're going to need to do that. So you might want to pause this video, open a new window in your browser, follow that link, and watch that, and then graph these piecewise functions, and then come back and sketch your graph on paper, and then I will put the one up here and we can compare notes. Give that a shot. All right, let's see how you did. So when I pull up my calculator and put in this piecewise function that has 3 different rules for 3 different ranges of x, this is the graph I get. So from 0, 0 to 2, 4, we're using the 2x. That's what's generating this line. Then from 2 to 4, f of x is 4. So that's the horizontal line going through the point y equals 4. And then finally, from 4 to 8, that's from here to here, our function is 1/2 x plus 2. So that's why this one is sloping up a little less than this one. This has a slope of 1/2, this has a slope of 2. My diagram might not be perfectly to scale, but it captures what's necessary, and this would be a full points diagram on a test. Notice how I've labeled the key points here. 0, 0 is where we start, and then it changes to the second function here at the point 2, 4, and then it changes to the third function here at the point 4, 4, and then the function ends at 8, 6. Notice how the range is not open-ended. We're starting our piecewise function at 0, go to 2, 2 to 4, 4 to 8. We don't go beyond 8. So this function doesn't shoot on down forever, and it doesn't keep going out there. It's just right here what we see. Okay, so having heard that, I want you to pause the video and write the domain and the range for this piecewise function. Okay, so this function is more complicated than the last function, but the domain and the range are way more simple. So we're limited. The function only goes from the origin to the point 8, 6. So the domain, that's the spread of the x values. So that's the horizontal. So we go from 0 all the way to 8. So the domain is 0, 8. The brackets are facing inward because it's inclusive. 0 is part of the domain, as is 8. So we're bracketing those because they are included. The range is very similar. We're starting with 0 for the y, and our furthest up we get with the function is 6. So the range is 0, 6, inclusive, brackets face inward. All right, now that you've watched the video, take a minute and jot down any remaining questions so you can bring them to our next class. Also remember, you can watch the video again. Maybe that will deepen your understanding. If you like the video, please click like and subscribe.